to introduce you to this paper, Global Analysis of the COVID-19 Pandemic using simple epidemiological models. So we have developed different models ourselves based on the SIR model. Very simple for everyone to be able to apply them to fit to the data and check the evolution, and also very important to check where the model fails. Sometimes it's crucial for us to understand that if the model fails, it provides a lot of information as well. So here it is the typical transmission dynamic system of 4 equations, where you have susceptible individuals that they may get infected, then they get infected, and then they get recover or die, right? There's no way back from any of these compartments. So we have susceptible individuals which get infected and then they recover or die. So for a total population, this is the 4th equation, where is the sum of all the susceptible individuals, the infected, and the recover. So for this, we do drastic assumptions to solve this analytically. For instance, we assume that the recovery over time is 0, at least during that initial time of the pandemic, and we solve the typical SIR equations, the system of equations, and we get a formula, an equation which looks like this. It's kind of a Fermi function equation where you have originally an exponential growth, and then it decays smoothly, what they call it the flattening of the curve, and this reproduces very nicely the data in China. You can see the total number of deaths as a function of day, how you have suddenly an increase of the curve and then a flattening of the curve. Obviously, the slopes of this curve will give us the deaths per day, and you can also get what we call the D prime model, where you get the first derivative of this function, which is this derivative here, and you can get how much how long the evolution, the pandemic will take in different countries. So we have done also other simulations, more sophisticated, like the extended SIR model or Monte Carlo grid or Monte Carlo Planck simulations, which give us a better understanding of the pandemic, of the evolution. And I'm going to show you to end this what our latest calculations show as for the 22nd of May for South Africa. This is very crucial for us to understand that these are statistical models. So the statistics so far is very low. Fortunately in South Africa, we don't have as many deaths as in European countries. And this is the prediction according to the data that we have so far, right? So there will be an asymptotic flattening of the curve around 6,000 deaths will happen in South Africa. Here we have the Monte Carlo simulation also, which agrees nicely with the death model. And I want to tell you that we have to be very careful. Here we go, because this is a similar plot for Spain. This is what we predicted on the 23rd of March for Spain, and you see almost 10,000 deaths. But then the model, the actual statistics, the actual deaths were more like 28,000, right? So the numbers may increase, and it's very risky to make any predictions at this point. So we have to consider that our predictions get better as we get more statistics. And here we have the deaths per day for South Africa as well. We are going to pick around 60 deaths per day, assuming that the statistics that we have are reliable, right? So with that, I thank you very much. I hope you enjoy the paper, how to fit the South African data, how to get the full width half maximum for your pandemic curve. And there are many things that you can do to predict the future. As I say, the future will be easier to predict the more data you have, like in any field. Okay, thank you very much.